All right, in 7.6, we're going to be looking at properties of equilibrium constant. And in particular, what this is referring to is the condition when you have a reaction that's actually going in the opposite direction. When you have a couple of reactions that are maybe multiplied by a common coefficient. And then lastly, perhaps when you're adding a couple of reactions together, what happens to the K expression in each of those cases? So that's kind of want to go over here with you in a little bit and kind of provide some explanation. So let's go ahead and begin with the very first one. So let me move this a little bit over to the side, and then we'll talk about the first case scenario. So the first case scenario that I want to talk to you about is the case scenario that involves the reversing of a reaction. So let's say that you've got this reaction, and generically, let me provide this example here. Let's say you got a reaction that is A plus B, and this is forming C plus D. Now, normally when you get the reaction this way, the K expression is referred to as the product of the concentration of the C times D. All of these are raised to, let's say that all of these are 1, just for simplicity's sake. Then the exponents are 1 all the way across. And I'll just put 1s here just to denote that we know that. 1, 1, 1, and 1. And then down here in the denominator, we'll have the concentration of A times the concentration of B. And both of these are 1 and 1. Now, just like we've got the reaction going this way, what we're saying, since we've got the products up top, what we're saying is that A and B, when they combine, are going to produce these two products, C and D. And in the forward direction, then we can express it like this, with this K expression. But what if the opposite is going to be true? So this here, let me just label this. This particular reaction here is in the forward direction. But what if it goes in the opposite direction? So instead of going to the right, we're going to go to the left, in which case C and D become our reactants. And so if I rewrite that equation, the equation then becomes C plus D going to form A plus B. And so simplicity's sake here, let's just use 1 for the coefficients. Now this reaction here would be the reverse of the first one. And so if you look at the expression now, and so let's put here reverse of the forward, we'll put K sub F just to denote K expression of the forward reaction. And then here, this is going to be K of the reverse. This is going to be equal to A times the concentration of B over concentration of C times the concentration of D. And since all of these have a 1, 1, 1, you can see quite literally here that the expression for the reverse reaction is the inverse of the first. And so typically one way that we can write that so we don't have to rewrite the whole thing is we can just take the expression of the very first one and we can write it as 1 over. And so if I do that way, let me go ahead and move this over a little bit this way. And so this reaction here at the far end, one way that we can write that is we can say 1 over the Kf, in this case, this would be equal to 1 over the concentration of each of these, which would be the value that we're going to be after. Okay, and so if we do all of that, that does allow us to kind of get into it in terms of the concept. And so let me provide you with one brief example. Let me put the problem up on the board, and then I can actually just go through the workup on it. All right, so here's a reaction at the bottom. It's the Haber process, but it's not balanced. So the very first thing that we're going to need to do here is to balance it. So you can see 2 nitrogens. We're going to need 2 nitrogens here, but we've got 2 hydrogens. We've got 3. So what we'll need to do is we're going to have to crisscross the subscripts for the H and the 3. That'll give us 6. That we want as a desirable. So what we do here to balance, we're going to go ahead and put a 2. Oh, let's move everything back. We're going to need a 2 here at the end. And we're going to need a 3 right here and a 1 there. Let's just be purposeful about the 1 coefficient. All right, so we've got the expression or the equation now. We've got it balanced. We've got a K value provided. And we want to know what's the reverse value. Well, in the forward direction, the value for the K value is 5 times 10 to the negative 1, which is not too bad, but let's see what the value is in the reverse. So the thing that we'll need to do here is if we want the reverse, all we really need to do here literally is to use that expression that we had up top here at the very top. We're going to take 1 over that expression. And so we don't need to write the expression out. But if I'm just trying to figure out k of the reverse, which we usually represent with a little prime hash mark here, or we can use here k to the -1 value, same thing. This is going to be equal to 1 over 0.5, and if you calculate that into the calculator, that gives us a 2. So here, what you want to be able to do is compare the forward k value. So that value is right here. Notice the value is 0.5, and the value of the k value for the reverse reaction is a 2. So typically what we want to be able to do here is to note or just observe that the reverse reaction is actually strongly favored because it has a value of 2. The forward one does go forward, but the number here for k, the expression value, is a little bit lower, so the reactants are going to be favored if we look at the forward direction. But if we look at the k value of the reverse reaction, then in the reverse reaction, that's actually going to be favoring here this product, which is going to be the N2H2, but in the reverse reaction, that reaction actually is quite different. Well, let's go ahead and write it down at the bottom. That's assuming here that we're going to get 2H3 going to form 1N2 plus 3H2. So you can see here that the product of the reverse is actually the reactants of the first, which is what the first k value was expressing to us, that it favors the reactants. Or in the example of the reverse reaction, it's the reverse reaction, which is going to be this reaction producing the products N2H3 moles of H2, which is also going to be favored. They just happen to be the same. So it depends on how you're looking at it from the vantage point of, are you going in the forward direction or are you going in the reverse direction of that particular reaction? All right, let's continue going forward here. Let's go ahead and move all this off to the side, and let's look at the next example. The next example is going to be looking at the idea here when we take a k reaction and we multiply all of the coefficients by a factor. Let's say that we're having a doubling of the reactants or something like that. We're increasing the overall concentration, but we're doing it proportionally. So let's say we start with this generic equation here, and if I go in here and I start putting coefficients A, let's put B, C, and D respectively, we can come up with an expression for this reaction. That expression would be C times D over A divided by, or A times B in the denominator, and each of these is going to be raised to the corresponding coefficients, like so. So the idea here is, if I'm able to come in here, and let's say that I'm going to go ahead and take this particular compound here, and I'm going to multiply this, say, times some number. Let's just say that I'm going to multiply it by, let's say, letter X. I'm going to multiply it. And this X could be a 1, a 2, a 3, etc. We don't know the number, but let's generically put X. Well, if I put an X here at the beginning and multiply this proportionally, all of these are going to wind up being multiplied by X, whatever that number is. So when I actually come up to my expression then, since all of that is already identified in the k value here, all I'm going to do now is to take the k expression as written, and I'm going to modify it so that expression then is going to be raised, the k value is going to be raised to the value of x. So all this means is I'm going to take this value here, and I'm going to take k, but I'm going to raise it to the exponent of x, is what this is meaning, or what all of this is going to entail if I'm going to be increasing each of the coefficients here by some standard multiplier. So if I do that for all of them, then the simple way of getting the value without having to do the calculations individually again is just take the original value for k, if you had already gotten that calculated, and then raise it by the value x, which is going to be the value that you're multiplying all of this by. And so that'll allow you then to be able to get all of that. the way you want, so it's proportional to all. So let's go ahead and put an example for us down here. Let me move a little bit, this information up a little bit, give us some space. And so down here, here's the example. Let me go ahead and put this. Let's say that we start with, let's use the same equation that we had used in the previous video. Let's say we got hydrogen gas reacting with iodine gas. And if this iodine gas is reversible, producing a product here, HI, and also gas. And let's say that we're given a K value here. Let's say that the K value is equal to 50. Now, first thing we need to do, if they're telling us that we're going to double the reaction, so this is a ×2 event, so this is going to be ×2 here all the way across. Well, the thing that we can do is we can just take this X or this K value at the very end. If we're following the rule that we mentioned earlier here in the example above, I'll take this K value and then I'm just going to raise it to the power. In this case, we're doing a ×2. So that means I can take this value here. I'm going to take 50 because that's equal to K. And then I'm just going to raise it to the exponent, which is going to be a value of 2 in this case. So what I'll do is I'll raise this to the 2 value. And if I do that, 50 squared ends up being here 2,500. And so very easy way to do this. So just keep that in mind that you want to be able to do this so that you can get to the outcome of the reaction in a quick and efficient manner, so you don't have to do all that extra work. All right, and finally, what happens when we have a couple of reactions kind of being added to one another? So let's go ahead and clear some space, move everything over here to the end, and let's go ahead and begin with the two reactions. Let me go ahead and write them on the top. All right, so we see we got reaction 1 coming in here, and in reaction 1, we know that A is going to go and form B. Notice it is a reversible. And then it's got its own K1 value. And then we've got a second reaction. So whatever the product was produced in the first reaction, that product becomes the reactant of the second. And that product then is going to undergo some reaction, some changes, and it'll produce the product C. So at the very end, we've got these two entities here. B ends up on both sides, and what that means is that B is a intermediary, or an intermediate product that is going to be produced in one, but it's going to be consumed in a later step. The example I'm showing you here is a two-step process for a given reaction. Later in the course, we'll talk about multi-step reactions. Provide a little bit of an intro here at this point, but the main idea here, let's say that I'm going to go ahead and add these two reactions together. If I add these two reactions together, a process that we're already familiar with is like terms or spectator ions. Well, if I'm going to add these two reactions together, what we typically do is we take a product form in one step. If it's used and consumed in a later step, we can treat them like we do spectator ions. And so we can cancel them out of the mix. And then we add the two reactions together. That'll bring the A, bring it down, and that'll bring the C and bring it down because that's the only thing that's left. And then we would have A producing C as the overall reaction. Now, what about the K values? Well, when it comes to the K values, now we're not going to be able to multiply them together because it's a fraction in and of itself. But what we're going to do with these two is if we want to add them, the way that you go ahead and add them for two reactions is essentially you're just going to multiply them. So what we're going to get here is we're going to get K1 multiplied times K2. And so when we do that, we'll get the overall answer. So we're looking for a product. So let's go ahead and give some values here. Over here to the left-hand side, let's just move things over just a tad. We use the same reaction overall. And so let's assume here that if we've got some concentrations provided to us, let's say here the K value, just to clarify here, let's say that the K value for the first reaction was K equals 2. And in the second one, let's clarify and let's say that the K value here is equal to 3. Now, if I'm going to do this procedure and kind of look at taking the K times K2, we're still going to get A equals C, or forming C product here. So what's going to happen is if I want to take this part here, I'm going to take the K1, which is a 2. I'm going to multiply that times the 3, and that will give me a 6 value overall. So the K overall is equal to a 6. And so that would be the way we calculate that. Now, individually, each step here is going to have a K value. So the magnitude is still quite high for the first step. It's still going to produce quite a bit because this is a K value greater than 1 by a factor of 2. But as soon as the second that product is produced and consumed, you're going to see that if I take these two, notice the overall magnitude is quite significantly high. So like I said, this is something that we cover later in when we talk about kinetics. We're talking about multi-step reactions, but here you do get a glimpse. If in chance you happen to have any questions that come up like this, you definitely want to pay attention to what we do or what happens when you add 2 reaction steps. And then we have to deal with the expression for K. We definitely need to make sure that we are taking these two and using this format here. Multiply the K values together for all of the reactions that you are adding. You want to multiply them together to give you the final value. And there you go. This is section 7.6.